Okay, so now, so I'll try to continue, and so I'll try to show that first, like parallel comprehension implies echelon 7. On complete separable metric space. And then, well, for simplicity, we'll just consider bare space, but the proof is just easily convertible for the general version. And the idea is using this kind of minimal pass principle. Well, actually, it's a bit different from the original proof in our paper, but hopefully it's simpler, so I'll try to show the proof. So let's say, well, given that f is, well, I'll use capital F for the function now. I mean, because I'll try to use a small FGH for a member of bare space. So if f is a lower semi-continuous function on bare space, we want to find a critical point. This is lower semi-continuous. Okay, so for that, well, we want to find a kind of a nice order on the initial segment of bare space. So for each sigma, we try to define, let's say P sigma is something like at least. So the idea is, okay, we try to approximate the value of R, but with some mesh. So I would say, let's say, just consider the value up to the level of 2 to the minus the length of sigma, minus 1. And so least this kind of number such that, well, L is just natural number, and there is H extending sigma such that, well, f of H is below this number. Okay, so that means, okay, we want to calculate the, well, inf of this f on the Kropen set generated by this sigma up to this level. And so this is real positive, so the value is just natural number. And then, okay. And then for sigma tau and at the same level, well, we'll try to define sigma is smaller than tau. Well, just compare the size of this. Define the order using this value. And this is, of course, well ordered, I mean, pretty well ordering on each of these levels. So then, AK, this minimal element in this, just the whole contour space with respect to this. Yes, so this minimal element. Then what we have to check is this. So then the value value of f at h, it's just more than info. This thing. I mean, so taking this minimal element, then okay, at each level, that's, well, minimal, and then so, well, calculating this number, so the, roughly speaking, level k approximation of the inf on each interval. So the inf of those is at least bigger than f of h. So it's lower semi-continuous, so this is, we can only say that this is smaller. We don't know whether it's equal or not, but yes. And well, I mean, checking this is not so complicated, but what we have to do is to, by the way, so this function is actually available because of the pi 1 comprehension. Here, actually, there's a set existence quantifier, and then the sigma 1 comprehension is essentially needed for this, but I mean, we have pi 1 comprehension, so that's still good enough. So I mean, so we can easily check that this is decreasing. Why? Well, because of course, I mean, k plus 1 is an extension of h of k. So the inf is smaller. And we always take a kind of a minimal element. So meaning that if here is something like that, okay, well, that is of course the inf. Well, so the inf of this has to be close enough to this one, and indeed, so we change the kind of a steal step by step, so it can be a bit more precise, but I mean not much different. So we can check this approximation from this minimality. I mean, easy check, and then once we have this, then because f is lower semi-continuous, fh is always smaller than okay. And this is more like a basic topological discussion. Okay, so because this is lower semi-continuous, so I mean f of h has to be, I mean, smaller than something. I mean, so if f of h is bigger than a, then h is a member of an open set U of a, let's say, f inverse a infinity, but this is open. This is open, so some h listed to k is in this open interval. So that means f of h is more than this one. So with this reason, okay, f of h is always more than inf of these then. But then we can easily check that h is a critical point. Critical point. I mean, g is more than h, then g is equal to h, and this is the definition was, well, what's that? So the distance between h and g has to be smaller than f of h minus f of g. Why this happens? I mean, if g is strictly below h, I mean g is not equal to h, then let's say k is a maths, I mean, such that, well, g raised to k is equal to h raised to k. So then the distance between g and h is just the 2 to the minus ky. I mean, that's just the definition of the distance function on Baire space. So that means f of g, so by this, so f of g, it has to be smaller than f of h minus 2 to the minus k. But on the other hand, we have this one. So p of g restricted to k, oh well, maybe we don't need big space. On the other hand, p of g restricted to k is just the same as p of h restricted to k. And so by this minimality, I mean level by level minimality, that means that so p of this thing has to be smaller than f of g plus 2 to the minus k minus 1. I mean, by this definition. So at each level, h is, f of h is always smaller than the, something like the in plus 2 to the minus that length, more or less. That's the needed situation. And so this has to be true. And that means, but this and this already contradiction. So g has to be equal to, h. I mean, that means h is a critical point. Okay, so it's this, like this, or kind of a iteration. I mean, and then consider a minimal element is this with respect to this order provides the critical point, provides a critical point. Just so in a sense, I mean, critical point of a lower semi-continuous function on a complete separable metric space can be still be understood by a, well, some kind of minimal point, some kind of a minimal path of a Baire space. That's the proof. And on the other hand, I can just continue using this. On the other direction, Ekman theorem implies bound comprehension. It's, Well, this is also, this can be also done just by using bare space. And then, okay, so pi on C0 was equivalent to the statement that given a sequence of 3, then you may find the kind of a information whether 3 is sorry, whether 3 is ill-founded or not, well-founded or not, or has a path or not. That's good enough to show that pi on C0. So okay, so for this, given a, well, let's say over AC0. But actually, assumption of AC0 can be omitted. I'll mention it later on. But, so the given a sequence of trees on bare space, and we want to know that each of Tn has a path or not at once, in a sense. So okay, so for given H, a member of bare space, well, we will just consider H sub I as the H of, what's that, 2 to the I plus 1 times H plus 2 to the I. So in other words, H is just the sum of, Turing sum of all HI. So 2 to the I part is HI. And then okay, well, so each member of Cantor space can be considered as a, sequence of a member of bare space. So we will define lower semi-continuous function f by just the 2 to the minus I. HI, it's not a member of PI, like this. So for given H, we will check that H sub I is a member of, is a path of Ti or not, and checking those things. And then if it's not a member of the path, then you will find a witness for that at some point, in a sigma 1 way. Then you will add that value to this. And then that defines lower semi-continuous function. From definition, you can easily check that the value is bigger than A, it's sigma 1 notion. F of H is bigger than Q, it's sigma 0, 1. So this is a lower semi-continuous function. Need to check it. Okay. So then, one can easily check that, well, so given H from bare space, and then if Ti has a path, let's say G, but Hi it's not a path of Ti, then we may consider H bar defined by what's that? H bar, I mean Hj how I would say, yes. Yes, so yeah, right. That's what I wanted, right? H bar j is Hj if j is not I, and the H bar I is just this G. Right, thank you. and then, okay, so H bar always below H with respect to this F. And this is not. So that means, so this means that what we have is that the H is a critical point. H is a critical point. It's just equivalent to saying that the H sub I is a member of Ti if Ti has a path. Right? So finding a critical point is just the same as checking whether Ti is you found it or not. Ti has a path or not. If H is a taken critical point, and define X as an I such that Hi is a member of Ti. Well, this is actually either one. So with it, just with ACA 0, we can find this X by arithmetical comprehension. We can find this X. Then for any I, well, I is a member of X if and only if Ti has a path. We have the proof. That's the reversal. And okay, so that's the main story of the why Ekran's theorem is equivalent to power comprehension. And indeed, so both direction is still true on Cantor space, but so if we both direction works, same argument works, I mean, same argument works on Cantor space, which is compared, but now the leftmost path principle or minimal path principle for Cantor space is just equivalent to ACA 0. And that's provable over RCA 0. So actually, while the minimal path principle on Cantor space is equivalent to ACA 0. So we also have a result at the but the reversal is actually not like this, but more like it just directly calculating the minimal path principle. But yes, so we can easily have the following equivalence. So the ACA 0 and the H-clan theorem for Cantor space for lower semi-continuous function. And so okay, so I work over ACA 0, but first you can work for the same thing for Cantor space over RCA 0. Well, for the case for Cantor space, we can easily do. We can easily find just well, unlike this argument, more like a just this style discussion provides a leftmost path. So that's good enough. Okay, and and sorry, so here I only consider the existence of a critical point and forget about the initial point. But actually, so the original statement, another remark is that the original statement was that if f is a lower semi-continuous function on lower semi-continuous, and then the original statement was something like for any h on bare space, then there is g below h, and the g is a critical point. That was the original statement. I almost forget about that initial condition. But indeed, you can always find a critical point below any point. That's the real statement. And then, but that difference is usually not big. I mean, when we consider lower semi-continuous function, because I mean, what's that? We check the question. But I mean, so this version is still equivalent to the. I mean, the point is that this is also provable with impermanence C0, because just given this f and h, then we may consider f tilde by saying that okay, so the what we have is that given h, so the point s, let's say g, such that g is below h, is a closed set. You can easily check. This is pi to 1 once h is fixed. H is fixed, and this is pi to 1, so this is closed set. So then we define f tilde as a new potential function by, so f tilde h is just f of h if okay, this is not great. If g is in S, and otherwise just the f of h, well, let's say h0 plus distance between G and H0. Hg is nothingness. So this function is also lower semi-continuous, and if dh, I don't know, h tilde is a critical point for any critical point of f tilde, it's again a critical point for f, and it's in S. It's a critical point for f in S. You can easily check it. So, well, I mean, lower semi-continuous function, you can always define a bigger value on any open set. That's the idea. So this is outside of S, it's just an open set. So you can always consider bigger value. I mean, make it bigger than this one. Anything is fine. So this is good enough. And okay. On the other hand, I won't give a proof for those. But what is interesting is that the difference of this kind of a precise version and the original version is just equivalent if you just consider lower semi-continuous function. But if we only consider the continuous potential function, then there's a difference actually. And I won't give a proof, but actually what we know is that the pi1 C0 is even well, C0, AC0, well, so pi1 C0 is still equivalent to say that for any continuous potential function on, okay, now it should be complete for any continuous potential function on any complete supermetric space. Now, sorry, I mean, actually, just bare function maybe not enough. But any continuous potential function and H in A hat, there is a critical point Z below X. So this version is still equivalent to pi1 comprehension. But proof is a lot more complicated actually. I can't show it now. But we can still prove it. We can, well, I mean, of course, the reversal is much harder. Constructing the counterexample is much harder, but we can show this. On the other hand, if we forget about this initial condition, then that's just ACA0. So ACA0 is equivalent to say that for any continuous function, just has a critical point somewhere. It's just provable within ACA0. In other words, I mean, finding the critical point in some complicated closed set is still difficult. even for continuous function. But indeed, I mean, it seems that I only checked very few examples of the application of Ekran theorem. Like well, very often it's more like finding some nice function satisfying some minimality condition to solve some differential equation, for example. Real use of Ekran theorem is something like that. And for that purpose, usually, I mean, the potential function is very often just continuous, while we need an initial point. That's really important, of course. I mean, we want to find a kind of a right stable point to solve some real problem. So for that purpose, probably this is the right version, but that's still equivalent to Baran comprehension. And another kind of trivial consequence of the Ekran theorem is the so-called Chalyst's fixed point theorem. And I'd like to see that one a bit. So, easy or almost trivial consequence of the Ekran theorem is called Chalyst's fixed point theorem. Says that, I mean, so A hat, the complete separable metric space, I mean, separability is not important for the original statement. And capital F is a potential function. Oh, the same thing. A hat to R positive, lower semi-continuous. And then let's say T is a transformation on A hat, satisfying that the T of X is always below X. Then T has a fixed point. I mean, of course, because the critical point of F is a fixed point if we know the Ekran theorem. But, well, I mean, on the other hand, this Chalyst's fixed point theorem seems to have been studied in a kind of a bit different context. And this can be considered as a generalization of a Banach's fixed point theorem, in a sense. Banach's contraction mapping theorem can be considered as a special case of this one. I mean, at least looks like. Well, it's rather hard to say what's the right version, right restriction of this is the Banach's fixed point theorem. It's rather hard to see it. But okay, conceptually, this is a generalization of Banach's fixed point theorem. And so this theorem is also studied. And of course, so indeed, the proof of this theorem can be also available in a very different way from Ekran theorem. Because, I mean, so forgetting about the situation in reverse math and then just consider general setting. And then the fixed point of F That's a very, very easy idea. But the fixed point of t can be found in the following way. So given just any point x0 in A here, and then define x alpha is on omega 1 in the following way. So x alpha plus 1 is just the t of x alpha, and x gamma is just the limit of a x alpha below it. Consider this kind of definition. And then we can easily check that by the lower semi-continuity of f. Then if alpha is bigger than beta, then f of x, which is which? X alpha is always bigger than x of. So the value of f is decreasing on this sequence. But of course, there's no omega 1 length decreasing sequence on the line. So at some point, f of x alpha and f of x alpha plus 1 is the same value. But that means that's a fixed point because of this condition. That's a fixed point. So in a sense, transfinite argument works well to prove it. But on the other hand, of course, it's an easy special case of the easy consequence of the Ekman theorem. And well, if we see this kind of thing, then you may feel that, well, some ordinal type of statement might be also available from this characteristic theorem. And indeed, that's true. And so what we know so far is that the over RCA0, so is this theorem or beta plus 1 beta 1 functions implies ATR0. Okay, given a lower semi-continuous potential, so the beta plus 1 means beta 1 function t, I would say. So this t is for characteristic solution theorem, this is anything. But if you just consider beta 1 function, that implies ATR0. On the other hand, if we see this statement more carefully, what we can notice that is so here's one theorem, and implies ATR0. And while what we can easily check is that the characteristic theorem for continuous t is just equivalent to ACA0. This is nothing difficult, actually. And here, what we can notice is that if t is a Borel function, or nicely coded in second order arithmetic, then characteristic theorem or Borel. This statement is I12, while the original Ekran theorem is pi13. And here's a major difference of the complexity. And indeed, Ekran theorem is equivalent to pi1 comprehension. And from that information, we already kind of know that Ekran theorem doesn't have any form which is equivalent to pi12, because no pi12 statement implies pi1 comprehension. Pi1 comprehension has to be pi13. That's kind of a well-known fact. So heuristic theorem is an easy consequence of Ekran theorem, but if you restrict T for some certain class of functions, that has to be weaker than Ekran theorem. And if you weaken to continuous function, that's ACL 0. And there are one function that's already above ATL 0. It's still open whether ATL 0 is good enough to prove this. I guess not, but the separation seems difficult so far. And what happens if we consider all Borel functions? That's probably the final question of this talk. And for that, just 10 minutes, so just very quick review of the idea. But I mean, when we want to consider heuristic theorem for Borel function, the point is that, okay, so if we consider, well, when we consider the situation, heuristic theorem is an easy direct consequence of the Ekran theorem. Well, Ekran theorem is provable from minimal path principle for pi1 comprehension. Then, okay, well, for Borel, probably what we need is a kind of a slightly weaker version of minimal path principle. And that's the notion, I mean, not for this purpose, but introduced by Henry Tausner, so-called the TLPP or sigma alpha LPP kind of thing. So I'll try to introduce the TLPP, that's this one, is the statement that for any Baire space you founded, let's say, I mean, has a path, and let's say alpha is just the order. Then, well, let's consider just above ATL 0 in ATL 0. General definition is still possible, but above ATL 0 for simplicity. If alpha is well-founded, alpha is a well-ordered and T is ill-founded, then there has to have a path of TH such that for any G, which is so-called sigma alpha pseudo minimal. For any, so this what this means. So for any G computed from, we will use this information T and the path H. If G is computable from alpha's jump of T and H, then G is not to the left of H. Or if we, if we also assume then we will order on each fragment of Cantor space, then G is, then we may see, so H is minimal among these things. So G is not properly smaller than H. So minimal path principle, almost the same as minimal path principle, but we only consider this area computable from these things. But the technical part of this definition is that actually H, so this H can be used for the definition of G, right? So we don't fix the region at first. Finding a minimal means finding a relatively minimal in a sense. Okay, you can find a point, and from that point, you can't compute anything smaller from it. And this situation, it's already good enough to think about the characteristic theorem for Borel function. And so that's what I want to say. And so the result is that okay, so this is now actually Paul Schaefer and David Fernandez Duque, and now together with Henry Tausner and myself. So the statement is that the characteristic theorem or Borel function is equivalent to DLPP over RCSO. And the idea of the proof is that actually proof can be seen as follows. So the Ekman theorem was very close to minimal path principle, finding the minimal path. On the other hand, so this is finding Ekman theorem is very close to finding some minimal path. And then on the other hand, if consider characteristic theorem with T is a Borel function, then that's one thing. And if this is a Borel function, then there is some alpha well order. By the definition of Borel function, there is some well order such that, well, T of x is always computable from alpha jumps of x, right? The definition of Borel function. So that means if we can find sigma alpha minimal, sigma alpha relatively minimal path, then that's not a critical point probably, but that's good enough to be a fixed point for this T, right? So in that sense, so Ekran's theorem for sigma alpha approximated version of Ekran's theorem is the characteristic theorem for Borel functions, more or less. So that's the idea of the proof, and then, I mean, well, the current published proof is much more complicated than this idea, but I mean, we can justify this argument more or less. And then we can show that TLPP is equivalent to characteristic theorem for Borel functions. But it seems now, I mean, I feel that there are more theorems above the level of ACA0 in general, even in analysis. And I'm very much curious whether there is a special, like, for example, TDE, I mean, special problem of partial differential equation, whose, for example, the existence of a solution already requires Pan comprehension or something like that. I mean, the result of Ekran's theorem seems to suggest that direction, and I'm very much interested in, but I mean, of course, finding an example is not so easy. So if you're interested in, I mean, and that's an attractive field. Okay, thank you very much. I'll try to finish my lecture now. Thank you very much.